So let's look at our first example of strong induction in action. So here we have a theorem, and this theorem says for all integers greater than 1, it's either prime or a product of primes. And if you haven't heard of primes or seen their definition, please see the side video. But in any case, we want to try to prove this statement here using strong induction. So let's go ahead and start out our proof. So proceeding by strong induction, we have to show a base case. And just like previously we saw with normal induction that there comes in two different flavors, you don't just have to talk about all natural numbers. Here indeed, we're not talking about all natural numbers, we're talking about those that are greater than 1. So similarly to how in that previous definition 2 of normal induction, we had the ability to prove statements for sets other than n, you can do the same exact thing for strong induction. So here, instead of showing that p of 1 is true, since the set that we're looking at is all integers greater than 1, the very first thing, the first rung on our ladder that we have to show is that p of 2 is true. So let's go ahead and define what our propositional function is. Because I've said it a couple times, but I haven't defined it. So you notice right here where it says n is prime or is a product of primes. So this is a disjunctive statement because it has an or right here. So it's really claiming n is prime or a product of primes. So that's our propositional function, n is prime or it's a product of primes. So as I said, our base case here is going to be 2 because it's asking us to show for all integers greater than 1. And the first integer greater than 1 is 2. So our base case is that 2 is prime or it's a product of primes. And thankfully that's really easy to verify. 2 definitely is prime. And so this statement here is true. And so we've been able to show our base case. And our base case here just happened to be 2 instead of 1 because that's the set that we're talking about, all the integers greater than 1. So now we get to the induction step. So for the induction step, we have to show this big ol' expression. And notice here it started at p of 1, but since we're talking about integers greater than 1, the assumption will look slightly different. We want to show that, well, we're starting at 2, p of 2 and p of 3 and p of 4 all the way up to p of k implies p of k plus 1 for all k. And if I were to try to prove this using a direct proof, that means that I get to assume this entire hypothesis. So I get to assume my entire hypothesis that every single one of these statements is true. And then all I have to do is try to show that p of k plus 1 is true. So what we want to show is that p of k plus 1 is true. Well, what does that mean? That means that either k plus 1 is prime or it's a product of primes. That's what we're trying to show. We use this assumption right here, and we want to show our conclusion And our conclusion translates to k plus 1 is prime, or it's a product of primes. Well, first off, if it turned out that k plus 1 is prime, we really don't have anything to show, right? Because if k plus 1 is already prime, then by definition of our propositional function, it's going to be true. If it's prime, well then, yeah, it's either prime or a product of primes. So there's nothing to show. That's not the interesting case. The interesting case is when k plus 1 is composite. So we're going to assume that it's a composite number, it's not a prime number. And if you watch the aside video, you know that composite numbers have a very nice property. In fact, k plus 1 right here, we could write it as a product of two numbers. So we know that we can write k plus 1 as a times b, where a and b are integers, and they are both greater than 1. Now, why does this help us? Let's think about this. Well, k plus 1 is equal to a times b. And so that means, in particular, k plus 1 is bigger than a, and k plus 1 is bigger than b, because k plus 1 is equal to their product. So of course k plus 1 has to be bigger than either a or b. So, put another way, a is smaller than k plus 1, and b is smaller than k plus 1. How does that help? Well, if these are numbers that are smaller than k plus 1, that means they show up somewhere in here, right? If they're numbers that are smaller than k plus 1, that means they show up somewhere inside of this big ol' conjunctive statement right here. And so, we know by assumption, since a and b, these things, since they're smaller than k plus 1, they show up somewhere in this big expression right here, and b shows up somewhere in that big old expression right here, and we assumed they're all true. That means p of a is true, and p of b is true. And what did p of a and p of b mean? Well, that means a is either a prime or a product of primes. And then b is also a prime or a product of primes. And so, if we have been able to write k plus 1 equals a times b, right? Because that's what we've written right there. That means that this thing is either a prime or a product of primes. And p of b being true means that it also is either a prime or a product of primes. So what we have is a product of primes or product of primes and a prime or a product of primes. So this here is definitely a product of primes. And since it's a product of primes, that allows us to conclude that p of k plus 1 is true. It's a product of primes, and by definition of our propositional function, that is true. And so you can see the power behind strong induction here, because taking advantage of the fact that this thing was composite, we ended up with two numbers. But we ended up with two numbers and we don't know exactly where they were. We know that they're smaller than k plus 1, but we don't know how much smaller than k plus 1. But thankfully with strong induction, since we assumed all the previous statements were true, we know that A showed up somewhere back in here, B showed up somewhere back in there. So strong induction allowed us to be able to use that fact to then be able to conclude our conclusion right here that k plus 1 is also a product of primes. So there's our example of a proof by strong induction.